Hey everyone, welcome back. Thanks for coming. We're switching gears from convex programs to complexity of counting and maybe also of other things. So welcome to Andrea. She's Andrea. I'm actually not sure. Andrea. Okay, thanks. She's a postdoc here at Berkeley. Take it away.
Hello, everyone. So I'm going to talk to you about fine-grained worst case to average case reductions. This useless acronym. This talk is going to rely heavily on some results from this paper, New Techniques for Proving Fine-Grained Average Case Hardness, with Mina and Virginia. But before that, I'm going to introduce very briefly fine-grained complexity and some fun, simple average case, worst case to average case reductions. So first, what is fine-grained complexity? So it's an area of complexity where we're really concerned about the constants in the exponent. So this is like n squared versus n to the 2 minus epsilon, so n to the 1.99. And an example of a hypothesis, which I won't define yet, but if you've heard of it, is the three-sum hypothesis that falls in this category. But we're also concerned about exponential differences. The strong exponential time hypothesis, also called SETH, is about the KSAT problem, and it's concerned about 2 to the n versus 2 to the 1 minus epsilon times n. So once again, this sort of concern about what exact constant is happening in the exponent. And our goal here today is we'd like to understand how hard our favorite problems are on average. And what we really mean by that is it would be nice to know explicit distributions on which we believe these problems are hard. And we're going to use reductions as a technique to understand what distributions some of our favorite problems are hard under. So what does this look like in general? You've got some worst case problem P, and we want to show that P is equivalent to potentially many different calls to some average case problem Q. And this average case problem Q is going to be drawn from some particular distribution. And the success probability of an algorithm solving Q is over both the randomness of that algorithm, the coin slipping, but also the randomness of the distribution. And so the crucial thing to remember here is if you have an average case algorithm with success probability 1 minus epsilon, it's allowed to be wrong consistently on an epsilon fraction of the inputs. So there's no way to sort of naively boost yourself out of this situation. If you shove in the same input that it was wrong on, it's allowed to be wrong on that input over and over again in the same consistent way. And I just want to note that this is different than randomized algorithms where if epsilon is less than half, you can sort of boost in a naive way of just plugging the same input over and over again and then taking the majority. So now we've discussed that, I want to talk about a really fun example of a worst case to average case reduction. This comes from a paper of Bloom, Libby, and Rubenfeld. And so here's the question. How hard is matrix multiplication on average? So first, let's start with worst case matrix multiplication. We've got some A and B, they're n by n matrices, and we're going to say that we're over some prime field FQ. So what's the average case problem? It's going to be the problem of getting uniformly random matrices over this field FQ. And what we're going to do to produce our average case problems that will solve our worst case problem is sample two random matrices, X and Y, from FQ. And our problems are going to be of the form A plus X times B plus Y, X times B plus Y, A plus X times Y, and X times Y. So a couple of things to note. Each of these matrices in each of these individual problems looks uniformly random. We've added onto an entry a totally random field element, and so it looks just like an IID random matrix. There are, of course, correlations between these different matrices. If you were to take the first and last, for example, you would totally determine the worst case matrices you plugged in, but each instance by itself looks totally random. And what happens here? Well, we can do some sort of classic inclusion-exclusion. We take the first, subtract the two second problems, and add the third, add the fourth, and you get back exactly the matrix you wanted. And so, what I want you to get from this fun example is both that average case reductions are super fun and you should do them. The other thing I want you to get is that we're making a bunch of correlated calls. Each call is indistinguishable from the uniform distribution or whatever distribution we care about, or potentially it'll have a small total variation distance. And then as long as you have a relatively low error, you can union bound across these various instances in order to show that you can solve your problem with high probability. This is a fun example. Now I'm going to talk a little bit more about some recent results and work in this area. So the highlighted results for the rest of the talk are going to be a framework that allows you to give average case hardness for worst case problems, as long as that problem is described by what we call a good low degree polynomial. I will also very briefly mention a new type of problem we described called a factored problem, where it turns out that the counting version of these factored problems have good low degree polynomials, and so you can get nice worst case to average case reductions. In the process of getting here, I want to tell you a bit of a story. And that story is about how you go from this paper of Volatile in 2017 to Boandasar et al. 2019 to our paper. And this paper is going to focus a lot on the cake leak problem. But especially in order to explain some of this Volatile work, I'm going to define some of the problems of fine-grained complexity that we care about. So what are the core problems of fine-grained complexity? There's Seth, which is the hypothesis that K-sat requires 2 to the n times 1 minus little o of 1 time. So this is exactly what I mentioned before. Here we're having a strong opinion about the constant and the exponent. And our K-sat problem, you're given a Boolean formula. It's in conjunctive normal form. Each clause is of size k. We also have the three-sum problem. You're given a list of n numbers. You can think of these numbers as being between negative n cubed and n cubed, if that sort of makes it easier to sort of internalize. And the hypothesis is that it requires n squared minus little o of 1 time. Once again, a strong opinion about the exponent. And finally, we have the all pair shortest paths problem. You're given a graph with n nodes and weighted edges. And we want to know the shortest path distance between all pairs of nodes in this graph. And the hypothesis is that this requires n cubed minus little o of 1 time. For all of these problems, we have algorithms that achieve 2 to the n times 1, 2 to the n times for sure. And for these other problems, similarly, we have algorithms that run in n squared minus some function that's little o of 1 and n cubed minus some function that's little o of 1. Great. So I'm going to tell you about some more fun problems and reductions. So first is the orthogonal vectors problem. You're given a list of n01 vectors, and I want you to tell me if there's a pair of these vectors that have a dot product of 0. And the hypothesis is that this requires, n squared time. And the fun fact is that this is implied by Seth. Next, we have the zero cake leak problem. You're given a dense graph with weighted edges, and we want to return true if there's a cake leak whose edges sum to 0. And the hypothesis is that this requires n to the k time. Note, this is like brute force, right? You're looking at every single clique. And the fun fact is that for the 3 version of this, so the 0-3 clique hypothesis, so about triangles, it's implied both by threesum and by APSP. So, this is sort of the world of fine-grained complexity. There's all these problems, a lot of them sort of brute force time, and many of these hypotheses are implied by the core hypotheses of the area. So in comes Volatile, BRSV 17. And their goal is they want to give a worst case to average case reduction from some of these really fun fine-grained problems that we care about. And they totally succeed. They're able to start from this orthogonal vectors problems that I described. In fact, even the counting version, so more plausibly hard, right? It's not just that you need to tell me if there is or isn't, but in fact, how many you have. So that can only be harder. And they're able to show that if this counting version of orthogonal vectors is hard, then computing this function FOV is hard. And they're also able to show for the zero cake leak problem that I mentioned that computing this function F0 cake leak is hard.
Are we supposed to know what the functions are?
No, I'm about to discuss that. Yeah, so what the heck are these functions? So these functions are just polynomials over finite fields that happen to, on 0, 1 inputs, have the exact same output as the relevant problem. And there's some polynomial over a finite field. And what they're able to show in Volatile using previous work is if you have any problem P and you want to generate a polynomial FP such that it has low degree, and you can compute your worst case input, your worst case function, orthogonal vectors, for example, from a call to FOV, then this problem is hard on average. And in fact, hard on the uniform distribution over this field size, this field of size Q. So, they get an average case hardness from the worst case. The problem with this is why do we care about this particular function?
Can I ask
Yes.
a quick question? Actually, so when you define the orthogonal vectors problem, is the conjecture that it's hard over every field, over some field?
So this is hard when, I think this is normally framed as being over the integers. Certainly any field of size larger than log n, you're going to be fine. We're like, if it's like omega log n field size, it'll be the same, because it turns out the instances where we can show it's hard from Seth are ones where the length of the vectors in the first place is that short. Probably you can get away with some, field sizes other than that. But yeah, this is normally thought of as over the integers. Right, so these have a nice correspondence to the worst case problems we cared about over 0, 1, but over this larger field size, they no longer have a meaningful correspondence. And so there's cool things that they're able to do with these polynomials. They're able to make proofs of work, for example. However, it'd be really nice to understand whatever problem we cared about. So it'd be nice to get back to 0, 1. And it turns out that there's further work that was able to get back to 0, 1 with K-clique. So I just want to walk through what the result is, and then I'll describe some perspective on how that result was achieved. So you have some problem, worst case counting K-cliques. So we're given a graph, every edge either exists or doesn't, and the question is, are there K nodes such that all K choose 2 edges exist? And it turns out you can turn this into some polynomial, f-clique, and then you can use some sort of standard techniques in order to show that computing this polynomial is hard over a relatively large field, a field of size about log n. And then it turns out you can take that and go back to counting K-cliques over Erdős-Rényi graphs. And this happened across a series of works ending in Boadicea 2019. So let me start by defining what this polynomial is for clique. So for f-clique, what we do is we sum across all monomials that are going to correspond to every possible choice of K vertices in the graph. And the monomials are formed by multiplying all of the K choose 2 edges, or the variables corresponding to the K choose 2 edges within that clique. So this value is going to be 0 for a given set of vertices if it's a clique, and it's going to be a 1 if it's not. So this is great. And
it's not the other way. Shouldn't it be 1 if I want to count K-cliques, don't I want 1 if it's a?
I'm sorry, you're totally right. I flipped that. It's a 1 if the clique exists, and it's a 0 if it doesn't. If some edge is missing, then that edge is 0, and it causes the whole thing to be 0. So the nice thing here is this is relatively low degree when K is small, right? So think of K equals 3. The degree here is 3, right? This is a nice low degree. We've been talking a lot about wanting low degree things. So now there's this step where it turns out, if you have some polynomial over a finite field, you can show that the average case calls to this polynomial over a finite field are also going to be hard. So here, it turns out for various reasons, we're going to need the finite field to be of size roughly log n. And so you can think of this as evaluating this polynomial when every single edge has some random value between 0 and log n. And if you, sort of prefer to think about this as a graph problem, you can even think about this as putting weights on all the edges between 0 and log n. And now the weight is actually corresponding to a multi-edge version of this problem, and we're counting the number of cliques in this multi-edge version. So this is all well and good, but this does not look like a k-clique problem over an Erdős-Rényi graph. And Wilderreich Rothblum go from here and sort of come up with a gadgety way to get back to a k-clique problem that's unweighted, but it doesn't look like Erdős-Rényi graphs. Instead, Bois-Dassara et al. Sort of take this version of the problem where you have weights on all your edges, and they try and get back to 0, 1. And they do this basically, we have many of the authors here, so they can tell me if I'm misrepresenting them, but by breaking these down as bitwise multiplications. So we have this example here of this particular triangle with weights on it. And we can, of course, instead think of this as a bunch of different instances of a k-clique problem, 8 in particular, corresponding to every possible bit multiplication. So we can multiply the higher order bits by looking at the question of whether or not there's a clique in the graph of 1, 1, 0. We can multiply 2 higher order bits and 1 lower order bit with the 4 instances formed by every possible choice of 2 higher order bits and 1 lower order bit. We can check the 3 instances of 2 lower order bits and 1 higher order bit by every possible combination therein. And finally, the lower order bits. And indeed, this is going to multiply out to the correct value. It turns out that 3 times 2 times 1 is equal to 4 plus 2. What does this look like in general? Well, if I have some graph and I've got a set of edges A and a set of edges B and a set of edges C, this f-clique polynomial is equivalent to multiplying across all the possible choices of cliques, the various edge values corresponding to that clique. And if you imagine creating one instance for every possible choice of grabbing an ith bit of all the weights in A, a jth bit of all the weights in B, a kth bit of all the weights in C, and then weighting appropriately by this 2 to the I plus j plus k, you now have a bunch of instances, and they're all 0, 1 instances of cliques, right? This is now just a k-clique problem. We're just counting cliques over 0, 1 graphs. So, in some sense, we're done. And there is something misleading I've done, which is, are bits of, random values between 0 and log n, IID 0, 1? And the answer is they're not quite, but BBB19 basically expand the size of their numbers into a larger field. And then it turns out those bits are, in fact, have very small total variation distance away from 0, 1 IID.
I got lost with the k-partite thing. So why did you, now you're starting with hardness now of counting cliques in k-partite graphs?
Yeah, it'll sort of be easiest. It turns out you can go from non-k-partite version to a k-partite version, and then it's sort of easiest to go from the
still
k-partite.
like
There's
you're still counting
an
a lot.
argument to go between the k-partite thing and not. So but the thing is there's a different.
Oh, this was the inclusion exclusion that we saw. Like we saw like a few high order, like 2 high order and 1 low order.
That was a bit
That was something else.
Oh.
But this polynomial is a different polynomial once you have k-partite, and this polynomial has very nice properties with respect to its bit expansions.
Okay.
So it's sort of self-reducible.
Yes.
What is the fraction of graphs that you need to solve the average case problem to get the?
That's a great question. So if you have numbers that have like L bits and you have degree D here, then you're going to have L to the D instances, and we're going to need success probabilities because we're going to union bound across all of these instances that go as 1 minus, like whatever, 1/3 times,
Does it depend on the K, or does it also depend on N?
Oh, it only depends on, so it depends on K in the exponent, and log N ends up showing up in the base of that. So it ends up being something like log N to the K squared, basically, instances that we're generating. Or really, Bois-Dassara et al. Are generating. Yeah, so the k-partiteness is coming in here because we want to be able to say that we're grabbing like the ith bit of a weight in A and the jth bit of a weight in B. And if we were like totally mixing the graph, it wouldn't be meaningful to say that the ith bit of a weight in A because we'd have potentially cliques that are all AAA edges. So this k-partiteness allows us to do this sort of splitting. And then it turns out to get, two general graphs, and from general graphs, you can do inclusion, exclusion arguments to get around the fact that like you sort of have these stray edges that exist everywhere that's not in a k-partite graph. So, you're able to start from a worst case counting k-clique problem and show that counting k-cliques over iterator graphs is just as hard. And it wasn't really about being in 0, 1 to the n. And it wasn't really about, it was about being in 0, 1 to the n. It wasn't really about the k-clique problem. So what was it about? It was about the fact that f was a sum of monomials that were all of degree exactly d. It was about the fact that it was d-partite in this way, so that we can say that like we're grabbing the ith bit of all the a-type things and the jth bit of all the b-type variables. We needed that d was not too big. As your excellent question asked, we have this overhead that's exponential in the degree of this polynomial. And additionally, we needed that the output of f and p were the same. We can sort of make this a little bit more formal by saying that a good low degree polynomial will have a degree that's quite small, so log n over log n. This is the degree needed in order to make the overheads in this algorithm subpolynomials. So it'll be n to the little o of 1. And in fine-grained complexity, we sort of ignore this. It needs to be strongly d-partite. We define strongly d-partite as being a function that has monomials all of size exactly d, where every monomial is formed by grabbing exactly one variable from each partition of variables. And finally, we need that this polynomial fp and the problem p run on the same 0, 1 input produce exactly the same output. And what do you get if you have all these properties? So if p has a good low degree polynomial, and you can think of this as being like if you sort of announce that p in fact roughly is a low degree polynomial, right? Over 0, 1, then if worst case p requires t of n time, the average case version of p requires t of n to the log n to the d time, as long as an algorithm succeeds with probability 1 minus 1 over log n to the d. And if you want to not have these values of d floating around, given our constraint on d, we can say that any average case algorithm that succeeds with a probability that's 1 minus 1 over a polynomial, regardless of how small that polynomial is, implies that the average case algorithm's running time will be the same as the worst case algorithm's running time up to a subpolynomial factor. And if you don't want to think about probabilities d, you can think about this very small polynomial probability as being the probability throughout the rest of the talk. So what's going on at a high level here? We go from a worst case problem p to some average case problem fp. And we go from this average case problem fp to the uniform average case of p by sort of doing these bit multiplication tricks. So I have gone way faster than I did in my practice versions. And I have already reached the end of this talk. So I can either conclude and then take 30 minutes of questions, or I have another set of slides about this same talk area that will take about 30 minutes. What do people prefer?
Why don't we at least pause for questions that can be broad ranging to see if there's what we have.
Yes.
Are there interesting cases of worst to average case reductions where the queries are uncorrelated or of some degree of k-wise independence, so that then the success probability can be a little bit better than you would get from the union bound?
Yeah, so in this Volatile 2017 paper, they have their various polynomials, like FOV, for example. And when they evaluated on some input I0, the way they end up showing that this polynomial is hard on average, they're going to be able to show a 2/3 success probability on average, implies a faster, worst case algorithm. And the way they're doing this is they define some new polynomial G, which is just equal to FOV of I0 plus Y times a random input plus Y squared times some other random input. So each of these inputs that are capitalized here are, n bit, n are, from FQ to the N. And these are, Y here is like some single value from the field of Q. And so G is now a univariate polynomial. And if FOV had degree D, then G has degree 2D. And now what they do with G is they note that basically that you can do polynomial interpolation. That if you're getting 2/3 of your point actually on this polynomial and 1/3 of your points off this polynomial, that you can take all those data points and return whatever G of 0 is with high probability, as long as you're getting 2/3 good quality points. And G of 0, as it turns out, is exactly the F of the I0 you wanted to compute.
So that's a nice case where it's not as if all of your average case queries have to be correct.
Exactly. But in a lot of these like reductions, you instead like spit out this large number of instances and have no real way to error correct that we know of. But I do think that's like an interesting direction to go in to try and improve this probability. Yes.
You mentioned something about input in factored form.
Yes.
Because I know you use that as a basis for some crypto system or something. What's that?
Yeah. So I can talk about the factored problems, and that's the sort of like 30 minutes of content. The basic idea is you can take these various problems of like orthogonal vectors, for example, and instead of having every vector just be a 0, 1 vector of length n, you split it into, a 0, 1 vector of length d. You split it into various pieces, each of size b, where you're actually allowing a set of potential values of 0, 1 vectors of length b. And then you sort of imagine that you're actually sort of representing in a compressed form all possible vectors formed by selecting one element from each set. And so we allow potentially 2 to the d vectors to be represented if you sort of densely filled in these sets. And despite the fact that this is like way more expressive than the original orthogonal vectors problem, it turns out it has a much lower degree polynomial representation. And so we're able to do these worst case to average case reductions for the factored version of orthogonal vectors. But the problem now is like you have this factored version that's very expressive that we can show is hard on average. But it doesn't mean that the orthogonal vectors problem is hard on average. And in fact, there's fast algorithms for orthogonal vectors in 0, 1 inputs. Like in the uniform distribution where you're selecting every bit IID, we have fast algorithms.
What about the worst case?
So the worst case of this factored form is like tightly matches orthogonal vectors. So the like it's n squared, like up to some polynomial factors, and you can get lower bounds from orthogonal vectors, and that's from Seth. So the worst case and average case of this factored form match, whereas the worst case and uniform average case of orthogonal vectors don't match.
In this average case, factored form can be used for some applications, let's say. But it's not necessarily you're saying how we're interested in the finegrain.
Yeah. So the problem, I'm being sort of fast and loose when describing it verbally. The problem is all of these are counting problems that we're showing hard. And so there's various ways to build like fine-grained. We know how to build various fine-grained proofs of work from this, but we don't know how to build fine-grained public key exchanges or anything like that from these worst case to average case problems. The fine-grained key exchange that exists is instead based on the decision version of like the like zero K-clique problem being hard. And that decision version, we don't know how to show hardness from the worst case.
So 30 minutes is going to put us pretty behind schedule. It's a big ask for you to think on your feet. Do you want to take 15 to 20 minutes? Is that a possibility, or do you want to break? If you want 15 minutes, go for it.
I'm going to give a brief conclusion of this talk, and then I will talk a little bit more about factored problems, and I will be done in 15 minutes.
Fantastic. Thank you so much.
Sorry for speaking literally twice as fast as in my practice. So the results in this paper.
We all have to relearn what it's like to talk to human faces instead of a screen. I think it's very understandable. Yeah.
The results we covered were a framework built on this paper of Bressler, Boandasara, and Brennan. And we defined this new type of problem, which I have mentioned but not defined, called a factored problem. And we're able to show a bunch of reductions from the various hypotheses I mentioned, all pairs shortest paths, three-sum set, to a bunch of graph and string problems. We also show that counting orthogonal vectors is easy on average. And this is what I mentioned earlier. So it's what demonstrates the fact that we shouldn't, in fact, expect a good low degree polynomial for orthogonal vectors. In some sense, this is an apology for the fact that we construct these factored problems. It's because we shouldn't be able to construct something like this for the problems we sort of hope to. We also, in that paper, show a reduction for counting to detection on average case zero K-clique. And we show average case hardness for counting any small subgraph. I also wanted to talk a little bit about some papers that came out that I think are cool, that are very related to this talk. So Hirahara and Shimizu have a paper on nearly optimal average case complexity of counting bicliques under set. And they exactly sort of work on trying to improve these probabilities. Instead of having probabilities that look like 1 minus 1 over some very large polylog, they get improved probabilities, but not quite over the uniform distribution. And they have various interesting things that show up there. Additionally, Oded and Goldreich has this paper on counting T-cliques mod 2, which in fact is like reproducing a result for the Bressler, Brennan, Boandasara paper. But sort of with a different twist or direction. But I thought it was sort of a fun repetition, as it turns out, of a result that already existed in the original paper. Yeah, so we just did questions. So let me talk a little bit about factored problems. Give me a second.
So I don't really understand why is that a bad outcome. You're saying like, too bad there's an average case. That's why worst case orthogonal vectors are uninteresting. And then you are able to come up with another format that you might be able to use for whatever. I mean, I don't understand why that's bad. That seems like a good outcome, but
that is a fair point. It is a good outcome. I'm always rooting for problems to be hard. But that's not very nice of me or something, yeah, I think you make a good point. It's great news, everyone. So just a reminder, the orthogonal vectors problem, we're given n vectors, they're 0, 1 vectors, and we want to return true if 2 of them dot product to 0. So here's the factored version. Instead of having these nice, vectors, we instead have every vector represented by multiple sets, each of which include vectors of a particular length. So here we have, two sets with vectors of length 3. In general, these are going to be, think of them as like root n sets, each with vectors of size root log n. Root log n sets, each with vectors of size root log n. And we define the notion of like what it means to be counting vectors over this, basically as imagine decompressing all these vectors. That is, U here is in some sense representing 4 vectors because it has 2 vectors in its first set and 2 vectors in its second, which are the combination of the first half being grabbed from the first set and the second half being grabbed from the second half of the set. If you count how many orthogonal vectors exist between all these different sets, when uncompressed, we count that as the count of factored orthogonal vectors. And it turns out you can do this a lot more efficiently than I just described. Instead of uncompressing things, if you want to compare U and V, you can simply go in and check whether or not there exist pairs that are orthogonal. Indeed, there are, like this pair, for example, and this pair. And then every possible choice of one of these orthogonal pairs grabbed with another orthogonal pair is in fact going to be orthogonal itself. And so you can simply count the number of orthogonal pairs in each of these sets and then multiply those numbers.
But that's not the, sorry, is this all happening mod 2? That's not the only way to get an orthogonal pair of vectors, right? Because I could get something that's even from the first and also, or odd from the first and odd from the second, and it would.
We're asking whether or not the dot product is 0, not over F2,
Okay,
but
it's all over the integers. Okay.
all over the integers. Yeah.
You said that earlier. Thanks. Yeah.
No, it's a great question. This sounds
Well, you can't have negative numbers. They could be -3 from the first half, and
we're
it's all 0 1
they're all 0 1 inputs. They're all 0 1 inputs. Yeah. So the fact that we're restricted to this, set of 0 1 inputs, which it turns out is hard from SAT, conveniently for us. Or inconveniently for us, allows us to do this trick where we're just saying okay, we need the first half to be 0 and the second half to be 0.
I don't mean that it's not good, that on the worst case it's hard.
So Andrea, I have just one question. So just so that I confirm my understanding, what is the dimension of the vectors produced from these sets? Is it 6 or 2?
6.
Okay.
Here, yeah.
Okay. Good.
And we allow this notion of empty sets, but they're sort of trivial in this case. And what we're going to do with them is the following. We're going to take these sort of uncompressed versions of these vectors, and we're going to create a polynomial. And this polynomial looks totally heinous, but the key is just to totally not have to look at that polynomial. Really, what we're going to be able to do is have a single degree come from this entire group of bits. So in some sense, the normal orthogonal vectors polynomial is going to have a degree that sort of corresponds to the length of its vector. Instead here, we're going to have a degree that corresponds to the number of these groups. And in some sense, what's going on is that we're pre-computing everything about what's going on within these groups of B bits within the polynomial. And then we're able to just multiply across these pre-computed pieces. That's a very hand-wavy way to describe what's going on, but that is in fact sort of the internals of what's going on in this truly heinous polynomial. So what do we get out of the end of producing these polynomials? What we get is that the average case version of this problem is hard. Yes. So I was trying to brush over this because these polynomials are a lot. So what this is trying to do is across all possible vectors, across all the groups, so there's G groups, we're going to take the strings represented in those groups and we're going to check if they're equal to 0. And we're going to say there's a 1 if they're equal to 0 and a 0 if they're not. So this is just like trying to be the truth value, like the Boolean.
G here is 2.
Uh,
So 1 to G is 2 for you?
yeah, G in our small example would be 2. Yeah. And in a sort of more normal case would be something like root log n. And the polynomial that corresponds is exactly a sum over multiplications over sums, where each sum is effectively pre-computing what these b-bit multiplications are. We are only including a pair of variables that correspond to whether or not the youth vector contains the string S1, so like the string A correspondingly, in its ith set, if we only include this multiplication of these two if it turns out they already dot product to 0. And so by sort of doing this pre-compute across all possible b-bit strings, we've saved ourselves this factor of b in the degree. And in exchange, we're sort of paying the cost by having this really like complicated, by comparison, problem that we're able to show average case hard. What we get out of all of this in the end is that this factored problem is hard on average from Seth. And these factored problems still have a lot of that same combinatorial structure that we use in orthogonal vectors. And we're able to get various graph and string problems hard. We're able to show reductions to show that those various graph and string problems are hard from this factored orthogonal vectors problem using basically the same techniques we use to show hardness for regular orthogonal vectors. And I think that's enough of a sort of very brief discussion of factored problems. So I will end this and let the next person come up, and hopefully they won't speak twice as fast as they did in their practice.
Yeah. So we're switching over to Zoom, I think. But further questions for Andrea while we do that? We had a ton of discussion. Oh, yeah.
So when you say you pre-compute for those pairs, whether they are, I guess here it's over the integers with nothing negative, it's the same as being pairwise disjoint. Right? And then when you say we pre-compute that, you mean you use a fancier set of variables that represent those inner products of blocks, and then the polynomial you constructed was a polynomial of those variables. Is that, did I parse that right?
Basically, so the new variables are representing sort of blocks of bits, and each monomial is only formed across multiplying several different blocks of bits if it happens to be the case that those blocks of bits all like represent bits such that their dot product is 0. So we're sort of doing the pre-computation across which monomials we happen to include or not include into our multiplication.
And separating it into those blocks creates that multipartiteness that you wanted for your strongly.
Yeah, the strongly departite setup.
Okay.
Yeah.
Thank you.
Okay, let's thank Andrea once more. And now